So just remember, the exam is on Wednesday. Um, yeah, so hopefully you have studied most of it by now, but just in terms of like prioritizing, check the practice exams, make sure that all of those questions make sense, then move to the workshop quizzes. And then after doing that, like yeah, like just go over the notes, some like the examples I did in class, and the exam should be there shouldn't be like any major surprises if you have gone over all of that. I still will have like some office hours on Wednesday, and I think Karuna the TA should have some tomorrow, or if I'm not mistaken, yeah.
What is the last topic that could be covered on?
Oh, it was polar coordinates. So there are like two problems on integration, and then the other four are like the chapter 14 stuff, like before integration. So yeah. So like yeah, after even like the stuff from last Wednesday is on the final. It is not on the second exam. Today, actually, it is not today. It's also new stuff, so it's on the final, but it does help for the stuff of the second of the exam because we'll start triple integrals, which require double integrals. So there will be a part where I do double integral. I mean, I'll be doing a bunch of double integrals today, and the sorts of double integrals I'll do will are similar to the ones on the second exam. It's just that for triple, you do need to do an extra integration. But in that sense, today is more related to the second exam than the last class on the Jacobian. So let's start with triple integrals. And we'll keep going, talk about that next Monday as well. But I'll kind of present it today in the way that's most useful for like also like the second exam stuff. So there are a few things that I will not say today so that I just say the stuff that's most relevant to the second exam. So what is going to be a triple integral? Okay, as you may guess, at least in terms of how you would write it, like you'll see three integrals, right? So if you do that, what that means is that you're going to be trying to integrate a function of x, y, z, okay? So when you do triple integrals, in general, like the functions can be depend on three variables. And just by analogy, I'll put dv here, okay? So compare these, like let's just compute this with the double integral. Compare this with so for double integrals, you had something of this sort, right? Like you had a function of x and y times dA. dA was you know, dy dx, or dx dy, at least in Cartesian, right? Like there was a version of this in polar. Um, okay, so just by analogy, what do we expect this to mean? So dA like just means like a small piece of area, right? Like a tiny area. That's how you should think about this. So tiny area. Or really infinitesimal area. That's another way you refer to these things. And so dV, the way you should think about this is like a tiny amount of volume, right? Or a very small volume. So what's going to happen for a triple integral is that what happens for a triple integral is that now you have a region of integration which is in three dimensions. It's like in like actual real space, you know. So it's no longer on the plane. So you have something like this. So like I'm trying to like the region refers not just to the surface but also to the inside. So if you think of the so R is now like a region in three dimensions. with the inside included, right? So it has actual like volume, like inside included. Not just the surface. Okay, and the idea is that, you know, to do the integration, you should imagine that dv, let me put it here next to this. dv, the way you should think about it is like as a small piece of volume, right? So it's a small, tiny volume. So like think of this maybe as some sort of like asteroid or some like, you know, some region in space, like within it's inside. So now you're chopping off like the asteroid into mini pieces, right? Into like ice cubes. So like so here you have like all these small cubes. Like this, or you have another one here. Okay, and these mini cubes have volume dv. So these are like, you know, you break the region into cubes or boxes. Into cubes of volume. Okay, so it's just that dv in practice is dz dy dx just by analogy. You know, so just like, so a regular integral is just dx, a double integral is dy dx, and a triple integral is dz dy dx. So that makes sense. And of course, like you can kind of think about the variations of this. So it's also dc dx dy, and this is also dx dz dy, and this is also dx dy dz, and this is also dy dx dz, and this is also dy what dz dx, right? Meaning that, you know, like in the same way in which a double integral in Cartesian, there are two different ways to integrate it. Because it's 2 factorial, I don't know if you remember factorial. So 2 factorial is 2 times 1. Triple integrals, now you have 3 things, dz, dy, dx. So it's kind of how can you place them in 3 spots. So it's 3 times 2 times 1, which is 3 factorial. So that's why you get 6 different combinations. In practice, like, you know, so there are 6 ways to do it. In practice, we will only do one of those 6 ways. So not that the others are not possible, but we just will focus on the one that does come up most of the times in practice. So this, like, you know, of all the 6 possibilities, the only one that we will really pay attention in this course to is this one. So this is the one that we'll use for examples, meaning that we'll integrate first with respect to z, and then we will integrate with respect to y and x. So this is the one we will use. But like, you know, theoretically, it's possible to do like a triple integral in these other alternative ways. And now, so you're integrating like, okay. So the other question is like I'm just giving you for now, like a bunch of things of how the integration looks like, you know, how you set, like how you write things down. Then you have to ask what is the meaning of this, right? So when it was a double integral, you were like I told you, okay, one way to think about it is as the volume, right, of the function between the graph and the region on the plane. When it's like a triple integral, that is not like a very convenient interpretation, because if you remember when you have a function of 3 variables, the graph, if you actually wanted to see the graph of a function of 3 variables, you need like a 4th dimension, a 4th axis. And then the graph kind of looks like a like you would call it like a hypersurface in 4 dimensions. So in a sense, this would be some sort of hypervolume. but it's not like a useful way to think about it in that way because we don't have access to hypervolumes, you know what I mean? So really, that is not that convenient in this case. So the best way to think about like a triple integral, which is closer to the other interpretation of the integration in terms of like a limit of sums, is that like an integral is always a way to add up things. That's like the main objective of integration. It's always sums. Like in fact, like the integral symbol is supposed to remind you of an S for sum. So like an integral is always like a way to add up things. So really what the triple integral does for you is to compute like a sum, right? Sum in quotes because there are kind of like infinitely many terms. So it's like a way to compute a sum of the terms of what terms? F times dv. So of the quantity. Okay. So just to give you two examples, which are kind of nice to keep in mind of how this gets used in practice. So one is F being like a density. So like here's an example of how this gets used. So example one, where F is like a density. So if you have thought about density, like in the physical sense, like it could be like mass per unit volume. That's one way to think about density. I mean, there are different sorts of densities, but like that's one of those. So it would be like mass per unit volume, right? So, if you want to give units to it, like, it has units of mass over units of volume. So it has units, the units of a density is like, it could be kilograms if you like, just, or grams or whatever. Let's say kilograms over cubic meters, like that would be one potential, units you could use for density. So what is one way to think about this problem? It's like, it is like, well, maybe you have like a 3D object, like it could be like an actual planet, or it could be like a chair, it could be something like that includes the interior. So you have like a solid thing. So you have like, but let's just say planet. So maybe the problem is that you want to find the total mass of a planet, right? So, and like the planet will be made up of certain different materials, like, iron, like carbon, other elements. So like the density throughout the planet is not homogeneous. So what you would think is like f of x comma y would give you the density at a given point on the planet. Okay, and so what is f times dv, right? What is f times dv? Well, it's density times volume, right? If you just think about it in terms of the units, if you do density times volume, the volume units cancel, so you should get something with units of mass. So F times dV is kind of like density times volume, which is like a mass. So this is like kind of like the mass of one of these tiny cubes, you see? So this would be like the mass of one of the cubes inside the planet, of one of the cubes. Okay, so if you integrate the density, right? So what would be the integral of the density times dV correspond to? It's integrating all the small masses, right? It's kind of like the integral of all the mini masses, right? Like the tiny masses that coming from all these cubes. And so that's kind of like the total mass. So like, let me put here tiny masses. So this would be the total mass of the planet. Is that making sense? Like so this is like a convenient way to think about the triple integral. It's like you're adding a bunch of things, like, you want the mass of an object, you cut the object into smaller pieces, like, and you kind of add them all up. It's just like these pieces are kind of like infinitesimal, like, because it's like a continuous sum. Or that's the same thing that, if you like you ever take a physics class, like that's how moments of inertia get computed if you have ever computed one of those. So if you have like a solid object, right? Um, like say you have like a scene in there and you want to find like a moment of inertia or things like that, then you say, well, you take like you know, you take a small piece of the cylinder, right? That has some inertia, like for inertia, you like say you want to compute the inertia with respect to the z-axis or something like that. So here's the z-axis. There's some distance of this mini mass to the z-axis, which we could call r. So you have like an inertia, moment of inertia associated to that piece, and then the total inertia is like add up all of them. So like the total inertia would be like the triple integral. Like let's say this is like a mass dm. So like the total inertia would be like the triple integral of like the moment is like mr squared, something like that for a point particle. So like it's just
MR.
no, but isn't it like it's r squared because I think it's uh mr would be what? It doesn't have the right units, right? Like mr would it's ms squared, yes. Yes, so like
Oh, you're right. One second.
so well, anyways, that's actually secretly like Newton has done like a triple integral because he had like proven like this shell theorem. Like so there's another huge story. Like, yeah, so when you study like the okay, so there's this Netflix show Three Body Problem. I don't know who has seen it. It's actually very fun. But so the two, like if you have heard about the two-body problem, that is what Newton solved. So Newton solved like the gravitational attraction between two bodies. Um, and he proved that it moves like a conic section. Like so so like say here you have the sun and here you have the earth. Uh, and one of the things you can prove, like if you study the gravitational force between them, is that, at the end, you can replace, which is what you do like many times, is you can replace the interaction as if they were point particles, right? So that means like, because what you can prove is like kind of like the, 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 the gravitational force exerted by the sun on the earth is kind of like the same, as that one done by a point particle, with a mass equal to the mass of the sun. Like, so there's like a thing that you have to prove for that to work, but like in order to do that, you have to do like a triple integral because you have to compute like kind of like all the forces between a tiny piece of the sun here and a tiny piece of the earth and add up all of that. And it's a fun I mean, it is like a fun integral in spherical coordinates, which we'll do. But you can do it after you learn after we talk about spherical coordinates. If you open like a physics textbook that proves the Shell's theorem, I think that's how it's called, then you'll see that it can be done. So but anyways, I'm just saying like that all these things about triple integrals, they are used to compute sums of things, right? So it's not, you shouldn't think about them as hypervolumes because that's not like a convenient interpretation. In fact, here's another, and after this, I'll stop doing all these examples and I'll tell you how we work with them in practice. Here's another example. What if you take, I will, is coming up next. So what if you take, let me put it in a box because it's actually a very useful one. And it can be confusing if you don't think about it too carefully. What if you take the function f to be 1, like so constant function equal to 1? Okay, so if you take f to be 1, what is a triple integral in this case? Like, let's think about that. So if you think of the triple integral as a sum, right, of all these things, it is a sum of the pieces dv, because there's like the thing in front of dv is just one. So it becomes like a sum of the dv's. Right, so it's kind of like a sum of the tiny volumes, right? So what does it mean to sum up all the volumes? It's just the total volume of the shape. So if you integrate the function one, you actually recover the volume of the shape. Okay, so this is just the total volume. And I'll show you this with a few examples in a moment. One of the reasons why triple integrals are useful is that they can be computed used to find volumes. How? Just plug in one as the function. Because if you remember, oh, a triple integral is kind of like a sum. Yeah, if you just put f equals one, then you're just adding up the dv's, which is just the total volume. Okay, so it can be confusing if you just think, oh, it's in volumes for double integrals. But that's really, the meaning of the integration is actually pretty flexible. So it really depends on how you're thinking of f, right? The triple integral is always, the interpretation is always a sum of f times dv. So if f happens to be just one, it's just like the sum of dv's. And if f is like, again, mass over volume, then it's just like a sum of masses. So like, like whether it gives you volume or mass or something else, really depends a lot on what f is. So in fact, like I think I had like a similar question one of the workshops, like if you wanted to think of in terms of units, the units of what are the units of a triple integral? Well, if you think about it in terms of a sum, it's going to be the units of f times the units of volume. So it will be units of f times volume, the units of the volume. So, I mean, that's length cubed, but like, depends on which units you use for length. So it could be cubic meters or liters or something like that. Okay, so depending like of the units of your physical quantity, then the integration will and just give you like a different thing. Okay. So okay, this was a little bit chaotic, but it was just to tell you that when you have a triple integral, it is not hypervolume that you're computing. I mean, you can think about it in that way, but it's not a useful way to think about it in those terms. It's more like, okay, depends on really what f means. Since we don't give particular meanings to f in this course, like then it's just like whatever it is, But if you were on like trying to figure out the meaning of f, like of the triple integral, then yeah, it kind of like bends its meaning to, to whatever like the f function means. So what I'll teach you today is kind of like how to do triple integrals in Cartesian. But again, we'll just learn it in this way, this dy dx. So it's not too different from what we have been doing before, because it just requires like an extra integration. So that's what I'll start with today. And I'll also mention a little bit of how to do it in cylindrical, which you'll see is more or less the same thing. It's just that you'll put like the XY bounds in polar. Okay. So let's just work out some examples. And again, I'll focus mostly in how to set up the integration, because once you set it up correctly, then the integration doesn't look that different from we have done. So okay. So let's do first Cartesian coordinates. So what that means is that we're going to have something like this. So the mostly we'll just do this one or these are the two that we'll learn in this class, meaning that we'll always integrate first with respect to z. Okay. It is possible again to integrate first with respect to x or y, but it's like that is a detour that it's not worth going into. So what will happen here is that you have like a region of integration which is in space. Okay, so you have a region of integration in space, kind of, I think about it like some sort of asteroid planet. And so if you're integrating first with respect to z, you know, what you're going to use are, before when we were doing Cartesian coordinates, like if you remember, we were doing like horizontal or vertical arrows. What we'll do now is like arrows which are parallel to the z-axis. So you use arrows parallel to the z-axis. And so the z bounds, because when you integrate with respect to z, first, that's what you would integrate for here. So you would. So the z bounds is just where the arrows exit and where the arrows exit. And so, sorry, it's where the arrows enter, where arrows enter. And this is where arrows exit. Okay, and I mean, it's exactly the same for the other one, so I won't repeat it again for that one, but these equations can depend on x and y, so they can depend on x and y. Okay, and then what are the x bounds, x, y bounds? In fact, let me redraw a little bit the picture to make it easier for me to tell you what happens next, because the way I drew it is going to be a bit too complicated for me to do a nice picture. Yeah, let's say that the region of integration looks like this. And so how would you find the XY bounds? So again, like think about it as an actual planet, so it's floating in space. So the thing is like these will make a shadow on the XY plane. If you just think about like you know, if you put like a light, like the sun or whatever, like a light bulb, like it would that along the z-axis, then the planet would have like some sort of shadow on the XY plane, and that is what determines the XY bounds. So let me draw something like this. So this is like the shadow of R on the XY plane. And this is determining the bounds. So the point is that to do a triple integral, the way we're setting it up, you first determine the z bounds, and for that you look at the region, and then for the xy bounds you look at the shadow on the xy plane. So that part is kind of like the same as finding the bounds for a double integral. So that's why like a triple integral is really like a double integral plus an extra step, which is like the C bounds. So let me put it like that in words. So like a triple integral. A triple integral is figuring out the C bounds. Or like a triple integral bounds are like the C bounds plus the double integral bounds of the shadow. For the shadow. Okay, so I'll do some examples now. To show you how this looks like, because once we have done a few examples, like it will make more sense, like what I'm trying to say. So yeah,
So for the double integral bounds, I feel like when we're doing double integrals where one can be integrals of the other.
correct. Yeah, like then the same rules apply. So you can, like, if you do dy dx, then that means that y can be a function of x. Or if you're doing the x dy, that x can be a function of y. So yeah, like it is when it's the double integral part, it is identical. You can use exactly the same ideas as before. So let's do like I'll do this problem in two different ways to kind of show you like the main idea. And here now this is finally where you do have to have a bit more of acquaintance with these quadratic surfaces that we had seen way at the beginning of the course, like the paraboloids, the cylinders, the spheres, the planes, all of these things. This is where really they get used to. So let's see why. So here's an example. Fine, set up a triple integral. For I mean, the function is not really playing much of a role. I just want to have something written down, put it inside the integral. So let's say the function is x squared y squared times z, or in fact, 2c. Let me put a 2 in front of everything. You'll see 1, 4. And r, okay, r is like the really important thing. So r is going to be the region above the paraboloid. So I'm writing it in a way that's similar to how it would be given to you. So at least you would get like the name like you would be told like, okay, this is like a parabola. And below the plane. Okay, so let's try to draw this out. the paraboloid c equals x squared plus y squared is kind of like a typical salad bowl that I have drawn before. So that's how it looks. And the thing is like, as a paraboloid, if you think about it as like a paraboloid, like that does grow indefinitely. And so I will draw the plane c equals 1. That is just the like all the points that are at height 1. So you end up getting something like this. So there is some stuff between, there is a region that is above the paraboloid and below the plane, which ends up corresponding to, I'll color it in a way that's useful for finding the bounds. I'll color it like this way. So it's kind of like the inside of like if you thought about it like a salad bowl, it's kind of like the inside of the salad bowl that I'm looking at. Does that make sense? Let's see it. The visualization why. So it is, all these 2-point integrals refer to 3D regions. So it does include like, the inside like of the, it's not just like the surface, what I'm trying to say. It's not like just like the shells, like is the actual entire inside of the region. So, or the inside of the surfaces. So if you have a triple integral, okay, so what are we going to put as a function? Just this one because it's the one that I gave you. Right? And that's the function. And then in Cartesian, you put dc dy dx, for example. That is one that we can use. So I'll put dc dy dx. Okay, and I'll put c bounds. So I want to determine the c bounds here. So to determine the c bounds, what you have to draw are now arrows parallel to the c-axis. So they look like vertical in these diagrams, in these 3D diagrams, but it's better just to think about them as being parallel to the c-axis. So I'll draw these arrows. Okay. And you just have to ask, okay, between which equation the arrows start, where do the arrows start, where do the arrows end? So all the arrows start along the paraboloid, if you think about it. So like the lower bound for the arrows is v equals x squared plus y squared. Is that making sense? And where do all the arrows exit? They all kind of pass through the plane. So the top bound is c equals 1. That makes sense. Okay, cool. So that's it. That's what I was saying. Triple integral are c bounds plus double integral. So now we get to the double integral part. So how do you find the double integral, like the bounds for the double integral that you get here? You have to think about what's the shadow, what is the shadow that the salad bowl makes on the XY plane, right? So that, like, kind of required a little bit of imagination, but what do you think? Well, maybe before I say it, any guesses? What is the shadow? Yeah.
Kind of like a circle.
Okay, it is a circle, good, with the inside included, because it is more like a disc, but yeah, the edges are determined like as a circle, right? So you have you see this circle here, right? And essentially the copy of that circle, like on the XY plane is what determines like the edge, like the end of the shadow. So yeah,
You basically like a level curve with the top down?
It is like a, in that case, it is like a level curve, yeah. You do have to look at the intersection between the two surfaces, right, which gives you like a curve. So, I just don't want to use level curve because we're not necessarily thinking, well, in this case, they're kind of both like functions, but you know, like sometimes like the surfaces could be spheres and things like that. So you don't necessarily want to think about them as functions, but yeah, like it's more or less like the same. So the shadow in this case is a disk. So the shadow is one. Okay, how do I determine this? If you notice these two intersect when do these two things intersect? When like x squared plus y squared equals 1. So this gives you like x squared plus y squared equals 1, and so the shadow is the unit disk. Is that making sense? So the question boils down then to how do you find the bounds for the unit disk in Cartesian, for example, which we had done before. But let me just remind you how that worked. You know, one option was to solve for y, for example. So you get y equals plus minus root of 1 minus x squared. So the xy bounds end up being identical to those. So what I'm saying is that like the triple integral does have like a part of solving it becomes identical eventually to, you know, finding the bounds for a double integral, and that is not that like it's exactly the same to the stuff that we have been discussing so far. So it's just like it does have like an extra initial step, which is like finding the C bounds. But after you find the C bounds, the problem, like the rest of the problem, in terms of bounds, is just like just doing the double integral. Is that making sense? Is there any questions about this? So just to show you that it actually is the same idea in terms of how the integral works. I won't do all the steps because I read like just take up a little bit of too much time. This does mean like integrate first with respect to C, pretending that everything else is like a constant. So that's why I put like a 2 here in front, so to make the numbers nicer. So it's like integrating 2z dc, that's just c squared, right? So like if you were to do like the integration, the first step would be from x equals 1 to x equals -1 to x equals 1, y equals minus root of minus x squared to y equals root of minus x squared of x squared y squared, and then 2c integrates to c squared, right? So you would get something like this, which is, yeah, that, I mean, just to do another step, it would be a bit, like in practice, like this is a bit too tedious to integrate, so, but I'm just trying to show you a little bit how this looks like. But something like that could be like something like that could be like the top. If you were to keep doing the problem, like, you know, that is the integral in terms of x and y that you would do, for example. Now, and this is like a good segue for like the other thing that I wanted to mention, like you see the XY bounds were like bounds for a disk. So like it's natural to say, why wouldn't you just use polar here, right? And you can actually use polar for the XY part, right? So there's like this thing called cylindrical coordinates, okay, which let me just mention it and redo this example using cylindrical. So there's this thing called cylindrical coordinates. And we'll do more examples about it next time on Monday. I'm just trying to kind of mention like the most useful things for, for the second exam. So in terms of the double integrals. So in cylindrical coordinates, the way you should think about this is like polar coordinates plus the z-axis. Polar plus c, which means that like here, you have like an integral for a function, okay? But, if you remember let's put it like this, like dv was dc dy dx. I should use like a different color here. So dv was dc dy dx. But dy dx becomes r dr d theta in polar, right? So what you do here in cylindrical is do something like f. Let me put it like this. So basically what I'm trying to say is that you apply polar coordinates to the xy part of the integral. Okay, so you apply coordinates to x and y. But keep z as z, so, and do nothing to z. So it's still like z bounds here. And then in this case it's actually r bounds. And then these are like theta bounds. So I'll show you how this looks in cylindrical, so that you can see what I mean by that. But it's really just like a hybrid between polar and the z-axis or the z coordinate. Let's see. So let's do the same, but in cylindrical. So let's do this for in cylindrical. Previous example in cylindrical. So what do I mean by that? So the function f was 2x squared y squared z. And so doing this in cylindrical just means like applying polar to x and y. So if you remember how polar works, x squared becomes r squared cosine square of theta, right? Y squared becomes r squared sine square of theta, right? And z is just z. There's nothing you do there. Okay, so f it's kind of like, again, polar plus z. So f in cylindrical becomes like 2 r to the 4 cosine square of theta, sine square of theta. Uh, Oh, sorry, I forgot about the C. I totally, like you should have, oops. Is that what you were asking me? Yeah, like, no, it doesn't disappear. It just remains the same, but yeah, like it should have been there. Thanks. So that is now what it goes inside the integral. It's just that you multiply by R because in polar you also multiply everything by R. So it's kind of like, in that sense, the same. So the integral looks like 2R to the 4 cosine square of theta, sine square of theta times Z, and then times the R that comes from polar. So there's still like an R coming from polar, and then dZ the R d theta. Is that making sense? So it's kind of like setting the integral like in a version of polar, but there's also a Z around. So you still, when you transition, like, when you write like the integral is cylindrical, you do have to multiply by an R factor because that's the same R factor that comes from polar. And then now to find these, the Z bounds are the same as before, but it's just that now you rewrite them in polar coordinates. So for example, Z equals X squared plus Y squared, but X squared plus Y squared in polar becomes R squared, right? So the lower Z bound is now Z equals R squared. Okay. And then the top bound is Z equals 1. There's nothing else to change there because there's nothing that depends on X and Y. So it's still Z equals 1. That making sense? And then the nice thing about doing it this way is that now the theta, our theta bounds, they are the bounds in polar for the shadow. The shadow is still the unit disk, right? So it's easy to find the bounds in polar for the unit disk. R goes from 0 to 1 and theta goes from 0 to 2 pi, right? So this is a bit easier now. So, is that making sense? So this, like, in terms of like setting it up, does look a lot nicer than the other one. The other one had there. Okay, questions about this? Okay, let me do another example. I'll do it in both ways so that you see, like, again, like how it looks like if you try to set it up in cartesian versus in cylindrical. So let's do another one. where R is the region. Let's see, above the XY plane. Inside the cylinder. X squared plus y minus 1 squared equals 1. And below the plane C equals y plus 1. So this is what makes up R. Okay. Because this, again, triple integrals, are some of the most confusing parts of the course just because like the pictures are 3D. So it does require an extra level of like, getting used to 3D pictures. So, the good thing is that good or bad thing, like they will be used a lot throughout the remaining part of the course. So there will be many problems where like they're just triple integrals. Well, like we'll see many of these different pictures. But yeah, like it is complicated because like you do have to get more comfortable with how to draw these things. But again, like there are some hints given to you in the sense that you're given the names of the equation. So like this, supposed to look like a cylinder. So you have to remind yourself like why is that a cylinder? So let's try to work out the region first. Because whether you set it up in in cylindrical or Cartesian, you need the picture of the region. So it being above the XY plane, this condition is not that useful in terms of the picture, just that don't draw anything that looks like going in a negative Z axis. You don't need anything there. So it's kind of like just to set up like the stage for where the picture starts. Now, the first piece of data, which is a little bit more useful, is that it's like you're looking at stuff inside this cylinder, right? So what is that cylinder? So if you look at it as an equation for x and y, that is a circle actually, right? It's a circle center, 0, 1 of radius 1. So you have here the point 0, 1. And you're trying to draw like some sort of like circle on the plane, right? But it becomes a cylinder because if you remember, we discussed this a long time ago, but if you remember, you get like a circle for each value of Z because there's no Z in this equation. So you kind of start making copies of you kind of make copies of all the circles, and that's how you end up with the cylinder. Okay, so this is the cylinder. Is that making sense? And then, okay, so you have the cylinder, like again, like the cylinder, strictly speaking, goes also under, like in the negative Z-axis direction, but I don't care about that because I'm just looking at the stuff above the XY plane. So I don't need anything with negative Z. And then there is this plane, which is Z equals to y plus 1. So how do you draw that also? Let's think about that for a second. So to draw a plane like this, you say, okay, this is kind of like a line, right? It's kind of similar to y equals x plus one. So think about drawing a line on the YZ plane. So what would that be? Like it has positive slope, so this kind of, like when y equals 0, z equals 1, so it looks like this. Okay. So that is the line z equals y plus 1. Okay, so why is it that I'm saying that this is like a plane? Because what happens is that you have copies of this line for every value of x, because x doesn't show up in the equation of the line. So you kind of make clones of the line. You make clones of this line, and that's how you end up with the plane. So the stuff that we're looking at is the stuff inside the cylinder, below the plane, and above the floor. So we're looking at kind of like this stuff in here. Okay, and this one does require maybe me showing it to you on GeoGebra, so I'll do it in a second. But is that kind of making sense? Like, and again, like it will take some time to get used to these pictures, but eventually they become a bit. There's not that many variations that you need to know how to do, but like this is, I'm giving you a bit of the classic ones, and next time on Monday I'll do some more classic pictures. Um, for finding the bounds and things of that sort. So let's see if I can. Here. Just to give you a better idea of what this is. Of this one. So let me drop this. And I guess I don't need that. So I'll just show the XY plane like with the grid. So we have the grid here. And then you can plug in the plane z equals y plus 1. Z equals y plus 1 is this thing that you see there. I think what I use like purple on the board. So that is the plane. Oh, it's kind of purple what I use. So you see, it's kind of like a line. It's a line on the YZ plane. It just you move it throughout the x-axis, and that's how you end up. You end up with the plane, and then you have the cylinder, which is x squared plus y minus 1 squared equals 1. Okay. So I don't know if you see it, like the region, the 3D region is inside the cylinder, so it's inside this bottle. You're looking at the stuff inside the bottle, above the plane, above the floor, right, which is the XY plane, and beneath this other plane. So think about it like some sort of like bottle, right, or like a house where like the floor is the ordinary XY plane. And then the walls are circular, right? Because they're inside the cylinder. And the ceiling is this purple plane. Okay. So that is, you're kind of like the 3D region you're looking at is this stuff in between those things. Is that making sense? How this looks like. And again, we'll do a bunch more example. This will be the last example I do today. But on Monday, we'll continue doing these examples then. But also we'll talk about other ways to do this. But okay, so how will you set this up? Again, I'm teaching you now like two versions to do this. One is in Cartesian and the other is in cylindrical. So if you do it in Cartesian, that means that you're going to do it in dz, dy, dx. So what is the function? The function is z over root of x squared plus y squared. And I want to do this in the order d dy dx. I'll put here d dy dx. Okay, so what are the z bounds, right? So the z bounds are the bounds for these arrows that you see here, right? So hopefully it's kind of clear that the arrows all start at the floor, which is the xy plane, right? Like the floor is the xy plane. So z equals 0 is the equation of the xy plane. So the lower bound is actually z equals 0 here. Does that make sense? Because like the region is between the plane and like the bottom of the region is the xy plane or the disk, but and the top of the region is this other plane. So in fact, the top bound for z will be y plus 1. Questions of Okay, and then what are the xy bounds? For that, you need to find the bounds. Um, you need to find the bounds for the shadow. So what is the shadow here? The shadow is that disk that you see there on the xy plane. So it is better to draw the picture because it's like a double integral. So like you should just draw it like draw the xy plane separately to have like a better like idea of what region we're dealing with. So like the shadow is just this disk determined by this circle. So for example, if you wanted to find the bound for x and y in the order dy dx, to do something like this, where what? So you can solve for y. So you can say that y minus 1 squared, 1 minus x squared. So y is 1 plus or minus the root of 1 minus x squared. So the the minus solution is a lower bound, and the plus solution is the top bound. So and x goes here from 0 to -1 to 1, right? So you see, there was like a double integral involved. So that is, for example, that is how the bounds would look like in Cartesian coordinates. Is that making sense? So how about in cylindrical? In cylindrical, you just have to apply polar to x and y. So let's try to work that out. So in cylindrical, first you have to check what happens with the function. So the function f was z over root of x plus squared plus y squared. But again, it's polar to x and y. So remember that in polar, x squared plus y squared becomes r squared. So in polar, the function, this just looks like z over r. That is like the function or cylindrical. Like I'm using those two as synonyms. Okay. So this is what you're integrating as the function now. But remember, there is this r that comes from polar in the integration. So you have to put r, and put it here, r, the r d theta. And then you also have to put dz. So I'm using that same color for r, the r d theta to indicate that they are related to this R factor comes from the polar part, basically. And then what are the bounds for Z? They're the same, but now they're rewritten in polar. So Z equals 0 is still Z equals 0. And Z equals Y plus 1. If you rewrite it in polar, that's R sine of theta plus 1. So that is the bound for in polar there. Okay. And then what are the R theta bounds? You have to find in polar the bounds for this circle, for this disk. So again, like this is like a, this part is kind of like a midterm 2 problem, right? Like, so let's just draw the circle again. We did this before. So that is how, that is how the circle equation is in polar is 2 sine of theta. So the R bounds go from 0 to 2 sine of theta, right? And the theta bounds go from 0 to pi in this case, because it's in both quadrants, the circle. Then we can just talk about this.
For the Cartesian, why is that something like?
Oh, for the X bounds, you mean?
Yeah.
Like the thing is like, this is a circle, for the X bounds, you have to ask what's the most negative, the circle has like radius 1, right? So it is centered at 0, 1, but it's still like the most it can move in the X direction is 1 or -1, if that makes sense. If not, you can just like, if you set y equals to 1, like yeah, you'll see that x squared equals 1 and then it's plus or minus 1. Good. And this like, and again, this part is really like a double integral in polar. That's my point, right? Like these two bounds. So that is how you, if you have seen this disk on the exam, like second exam, this is how you would set it up, right? Like in these triple integrals, the way we're doing them is there is a double integral part that is identical to the stuff we have been doing, and then there's like the Z bounds, which is new, but not that different from what we have been discussing. So what I'll do next time on Monday, because again, Wednesday we have the exam, is that we'll keep doing this, but we also discuss spherical coordinates, which are like the more complicated ones, as Cartesian and cylindrical are not too bad. So we'll talk about spherical, and we'll keep doing examples, and I'll show you how the bounds look in cylindrical and spherical and Cartesian and so on, so that you get used to all of them. But yeah, so we'll be doing a bit more examples on Monday. Okay, so let's end here because it's almost over the time, and I'll see you Wednesday. Remember to try to come a bit early before the exam starts, like so, like you have all the 80 minutes. So